two were translated in the books, and the last two are ones that I thought we needed in the homework or to prove some of the things they left out in this section. You'll notice they have a lot of comments. It is left to the reader, or you can easily verify. We're verifying those starting today. Okay, restatement. Oh, wait. Let's do. So let's do our restatement. This is chapter 5, Theorem 5, chapter 15. So go find chapter 15. Theorem 5, it's on page 151 in the textbook. We're trying to translate it out of groups and normal subgroups to rings and ideals. So wherever we see a normal subgroup, we're going to call it an ideal, because we learned last time that ideals are the complement of normal subgroups. And then we're going to call groups rings. So according to that first phrase, it says let G be a group. So we're going to let G be a what? Be a ring. And H, a subgroup becomes a subring of G. Yeah, it didn't say normal for this one. Then it said there are two things that are happening. And the first one is HA equals to HB if and only if what? Is an H, and we don't have to change that. Yeah, and the second one is equals to H if and only if A is in H. Just using the fact that they're equivalent structures, we can rewrite this theorem. Do the same thing with theorem 1, chapter 13. Translate that one, and then and do this in your notes. Well, let's do it all together. Tell me what theorem 1, chapter 13 becomes. So let's go find chapter 13. As A ranges over G. But the cosets stay the cosets, right? So we have to just say that G is a ring. Is a partition of G. Now, was there anything that we had special about H? Was H a normal subgroup? Did they say in the paragraphs before that? H is a fixed subgroup. So the family of cosets HA, let's put that up here. Let H be a subgroup, sub what? Subring of a ring, of a thing, of a ring G. The family of all cosets HA is A ranges over G, and we can now take this part out.
Can you take out the T after the G on the first line?
Yeah, that's going to be there. Is a partition of G. So our cosets still give us partitions. Now let's look at theorem 1, chapter 16. Okay, what are, in this case, what is G, first of all? Let's start with G. Yeah. Let G be a ring. And they are talking about quotient groups here. Quotient groups come from a special subgroup. yeah, we're going to have ideals here because they come from normal subgroups for quotient groups, so the quotient rings have to be from ideals. So, and let H be an ideal of G. Then we can copy the rest of it down. Let F take a G to H be a homomorphism with kernel, I'll write it this way, kernel K. What do they conclude? F of A equals to F of B under what conditions? KA equals to KB. We're actually going to need that for one of our theorems that we're going to finish proving that they didn't actually finish proving. And then theorem 2, chapter 16 was also useful. Here again, what are we assuming? This is our fundamental homomorphism theorem, which they gave us. So we'll just go through the practice of rewriting it. They actually restated it for us, but let's practice. What do we need to know about G and H? Will G be a ring? And H, what? An ideal, the equivalent of the normal subgroup. H is an ideal of G. Let F take G to H be a homomorphism of G onto H. Then what's our conclusion? If K is the kernel, then we have H is isomorphic. I actually have not made a shortcut for that one yet. I think that's isomorphic.
Where did you buy that?
It's under the binomial, sorry, not binomial, binary operations. And it's right under that funky background
No,
one.
I always use the wrong one.
It's under binary relations. Is isomorphic to, where am I? Okay, G mod K. And there's our fundamental homomorphism theorem. Now, why can't we just go ahead and restate these without actually having to reprove them all completely? They're only relying on the properties of addition. These theorems that we've done only rely on the properties of addition. So we don't need to know anything about multiplication, therefore we can just restate it. Even though we're adding multiplication to the mix, we're not using it. So these have the same theorem statements, we just translate subgroups to subrings, groups to rings, and normal subgroups to ideals. So that's what happens. We don't need it in claiming the kernel of F as the isomorphism property right here. We don't need it. We only need the addition property to get the isomorphism. Prove it. Come to my office after class, we'll prove it. We'll prove it so you see why I say what I say. In other words, it's not clear to you, so this would be one you'd actually need to prove to see why that claim is. So if you don't see that in the proof, they're only using the addition properties of the homomorphism, then you need to prove it to see that. So you would actually have to go through the proof of that to see that claim. come to my office and we can do it. But I'm not going to do it in class right now because we have a lot of other stuff we have to prove. And we're not going to get through all of it. You'll see, I'm hoping to get through 2 of them here in 25 minutes. 6 and 7 down here, we're going to work on Tuesdays the extra credit projects to finish out the information from this section. All of it's going to be fair game for test questions. I've already garnered numerous test questions just from this section that I really like. So I would make sure I know this stuff and get it compiled into your notes, even if it doesn't make it in there right now. The first one is look at the proof of Theorem 2 in Chapter 19. It says that A mod J with coset addition multiplication is a ring. If you look at the proof of it, it takes them about 5 lines for it. You haven't finished it. So we have to finish the proof of Theorem 2. So compile this with your notes. You're going to take this and stick it back in with your notes, which if you wrote down the proof from the book, only it was partial. It wasn't complete. So we're going to finish it. You're going to just tack this on to the end of your notes. Cut and paste it. Okay, so what did they show in the book? They showed the 0 element, so you have the additive identity. And they showed the negatives, or the additive inverses. But what are they missing? To be able to show it's a ring, not a subring. They say show it's a ring. Yeah, they haven't done multiplication, anything with multiplication. And they haven't done associative properties of anything. So, let's start with, first of all, have they showed that it's closed under any of the operations? No. Let's start with closure. What?
They didn't do much.
No, they didn't. They left a lot out. Okay, so how do you show it's closed under addition? We have to get 2 elements and add them together, right? So what are elements in A mod J?
J.
Yeah, we're going to call them J plus A. Because when we're talking cosets, we're using the addition notation for it. Let J plus A and J plus B be in A mod J. Let's add and multiply them together. We can do them according to our definition. What is J plus A? I wanted addition first. And plus J plus B. What is that equal to? J plus A plus B, right? Mm-hmm. And that has to be in A mod J. Why? Since A is closed, since A is a ring, huh? It's closed under addition. So J plus A plus B is in A mod J. Now tell me about the multiplication. J plus AB. I claim that that's also an A mod J. Why? A is a ring, so it's closed under multiplication. So remember, when you're defining it, you're adding to it every element from your original ring. You're going to have duplicates, that's okay. But it has to be in there. So our conclusion, thus A mod J is closed under both addition and multiplication. And here we're using coset addition and coset multiplication. Now let's show associative. Addition and multiplication. We'll do them both at the same. Again, since A is a ring, and hence the associative property holds for both addition and multiplication. Let's see, we're going to have j plus a plus j plus b plus j plus c. And associative means that we have to have some of these grouped together. So let's group the last two together. Tell me what that's going to be equal to.
J plus A
Yeah.
J plus B plus C.
J plus, let's group these together, b plus c. Now, what is that equal to? J plus A plus b plus c, and I'm going to keep those last two grouped together. Now we can associate those together. We don't need two equal signs.
Do that before.
Yeah. I must like equal signs today.
It's more than equal.
Yeah, it's very, very equal. But then this would become equal to, and now we just change who gets associated together by the associative property. That makes sense? Yeah. And then we can break this up as j plus a plus b for our first group plus j plus c, right? But that's equal to j plus a plus j plus b, and then outside plus j plus c. So that makes it associative for addition. And now I'm just going to copy and paste, because the only difference between addition and multiplication is the signs. So let's just go through and take them out. And it's just the signs between the two groups. Yeah, that one stays, doesn't it? I got the wrong one there. That goes away, and that goes away.
So should the plus go away between the second and bottom bracket?
Yeah. Okay. And therefore, A mod J satisfies the associative properties for addition and multiplication. Now, we have to show commutative, but commutative we're not assuming for multiplication, we're just showing for addition. So how do we show addition as commutative? What does commutative mean? Changes order. We reverse the order. So we have j plus a, we want addition, j plus b. Apply that, that becomes j plus a plus b, but since a is a ring, it satisfies the commutative for addition, so we can have b plus a inside our parentheses, and then that becomes j plus b plus j plus a.
Why do we have to show multiplication?
Because that would be a commutative ring. We don't necessarily know we have a commutative ring. We just know we have a ring, which means commutative for addition.
Would it be commutative or not?
Only if A is commutative. Because you need to be able to switch the order of B times A and A times B. You can only do that if you know that A is commutative. So you need, if A is commutative, then your cosets are commutative. Thus, A mod J satisfies the commutative addition property. So we've done associative for addition multiplication, we've done commutative for addition. They did the additive identity and the additive inverses, so we have just the distributive property left to show. Again, I suspect we're going to need to use the fact that A is a ring. And then let's look at them. The distributive property says J plus A times J plus B plus J plus C. And we have to distribute that. So do what's inside the square brackets first. So what's inside our square brackets? When you add those together, you get what? J plus B plus C. And now you're multiplying that with the J plus A outside, and what you get? J plus what? A times B plus C. But what is that equal to? Since A is a ring, the distributive property holds, and that becomes J plus AB plus AC, right? But now we can split that up as J plus AB, just splitting up the addition here, J plus AC. But then break that apart, and that becomes J plus A, J plus B, plus J plus A, and J plus C. Now we have to do it the other direction. We don't know. Yeah. If we could have proved commutative, we'd be done. So let's change the direction on it. Just copy and paste. And then that means that this A goes to the other side over here. And you're going to have BA and CA. And so this becomes BA over here, and CA over here, and then this becomes AB, and this is an A, and this is a C, and that's an A. What is our conclusion? Therefore, A mod J is a ring under coset addition and multiplication. So that was just showing something is a ring. You see why they skipped a whole bunch of those steps. Now, let's look at theorem 3. They didn't prove theorem 3 at all. It says this function is easily seen to be a homomorphism. So let's look at theorem 3. It says A mod J is a homomorphic image of A. How do you show something is a homomorphic image of something? Find a homomorphism that it's onto. So we must find a homomorphism from A onto A mod J. The book suggests that we use f of x to be equal to what? J plus x. The x comes from our A right here, and J plus x is in our A mod x. We must show that f is a homomorphism. How do you show it's a homomorphism? Yeah. No, We're assuming A mod J is a ring. So we have to start with two things in A. Let A, B, how about that, be in our ring A mod J. Sorry, I was thinking A to A mod J. We have to go from A mod J to A. So what should we call these? J plus A, J. No. I was right the first time. Yeah, let A and B be in A. Then where does F take them? F of A is equal to what? J plus A. And F of B is equal to J plus B. So now, let's calculate F of A plus B. That would be equal to, according to the definition, J plus A plus B, correct? But according to coset addition, what does that become? J plus what? J plus A plus J plus B. Which equals F of A plus F of B. Yeah, not bad at all. And let's do the multiplication. F of AB, according to our definition, this is J plus AB. Apply the fact that this is coset multiplication, and we get J plus A, that's capital J, times what? J plus B. Yeah, that's equal to F of A times F of B. So what's our conclusions? Now we have to show onto. How do you show something is onto? Start in the range and find something in the domain. So what do we want to start with in the range? What would you like to call it? J plus Y. So let J plus Y be in A mod J. What do we think in A gets mapped to J plus Y? Yeah, then Y in A satisfies F of Y is equal to J plus Y, and hence F is onto A mod J. What's your conclusion? Therefore, A mod J is a homomorphic image of A. To be a homomorphic image, you have to show a homomorphism that maps onto it. No one knows that. We saved the much more entertaining ones for Tuesday next week. Part of it is a homework problem. I think it's embedded in number 8 is one of your homework problems. It's like a little sub-property. It's either, I don't know why there's two number 8s. I think it's part of this last number 8, not part of the first number 8, is part of a homework problem. Huh. Someplace it's not counting right. Oh, that's where the counting is off. There we go. Now we got it fixed. Okay, I will post this actually not in the PDF format. I'm going to post it in LaTeX format. Update your notes. You're going to need the rest of these in your notes because your notes are incomplete because the book was incomplete in making them. But you need these in your notes. And then when you go to graduate school, what we're doing in class today, you would have done automatically on your own. That's part of reading your textbook. For those of you headed to graduate school. Some of you are headed to graduate school. I've talked to some of you. You'll do fine. All of you could do fine in graduate school if you put your mind to it. You just have to determine that you're going to do it.